Hi, I'm Antonio Sale, and in this video we are going to continue our discussion on controller structures in which we have an excess of manipulated variables, of actuators, say one primary control variable and two manipulated ones. In a previous video, we motivated the interest of this discussion, presenting some examples of processes needing to think in this. And we also reviewed some basic strategies in which just one control loop was tuned to be in normal operation, and then we could split the power via some load balancing setup. If one of the power sources was much cheaper than the other one, we could use split range, heating with solar energy until we saturate and we need to burn natural gas, let's say. But split range and load balancing in very complex situations may need even real-time optimization, scheduling the power generation in Spain to meet the power demand is not an easy problem. But okay, heating a mixture of two reagents is somehow easier to think of, and we can, either split 50-50 or use one heater or whatever. But, things may get complicated in large-scale scenarios. The last of the options we reviewed was override control, in which basically this was a sort of split range, but in which we allowed for degrade behavior, and only when an emergency situation arose, we decided to connect the extra power, the extra manipulated variable. So override is kind of fail-safe backup. But well, in all these things, there was only one controller in charge of the feedback strategy. We will now discuss situations in which we will devise additional controlled variables with additional set points for them, and those will be cascade control with extra actuator, with extra manipulated variable, gradual control, and a double cascade combination of these two things. In order to make things easier to apprehend, we'll discuss all of them in the same case study process as follows. So we will consider this kind of two-tank setup in which we wish to control temperature at the outflow pipe. So we have here a temperature sensor that transmits the reading to a temperature controller, receiving some set point. So the thing is, what do we do now? We have two manipulated variables, but the thing is that this load balancing and split range stuff was reasonably easy if the two actuators had a similar bandwidth, let's say. The effect was similar, so switching one off and turning the other on or whatever were sort of interchangeable. But in this case, that does not happen. So with these strategies, we may have stability of performance problems. In this case, tank 2 is small, so this resistor is able, let's say, to quickly heat the water in this tank. But this steam supply to this heat exchanger has itself a lot of thermal inertia. We need to heat a lot of metal parts before actually heating the water, and then we have some delay with this flow, some residence time on tank 1, and we need to heat tank 1 before heating tank 2. So the step response of this manipulated variable 1 may be very sluggish and taking a lot of time, but manipulated variable 2 may just have this step response much faster. So in this case, performance is very different from using one actuator or the other, and then naive load balancing or split range may not work as desired. So our first proposal will consider what is called cascade control with extra actuator, with extra manipulated variable as follows. Our primary temperature controller will decide the voltage to the resistor, say between 0 and 220 volts AC, and this will be our main controller because, well, we assume it is fast. But however, it may saturate. We have not such a big resistor, and then if it saturates, then we need to activate the steam supply. But the thing is that we may do it as follows. This thing, which is the command of this master controller, will be compared to a manipulated variable to set point, say for instance of 110 volts, center of its range. Then in that situations, let us analyze what is the meaning of, let's say, that the fact that the resistor is operating at 200 volts. It means that incoming water to tank 2 is very cold, so we need to heat a lot. Then, if my resistor is significantly above its desired central point, it means that incoming water is too cold and we should open a little bit the steam supply valve. So we will tune a voltage controller and then it will act upon this steam valve. So if resistor is operating for a long time at high power, it will open the steam supply, and on the contrary, if the resistor is almost switched off for a long time, then it means that we are heating too much. So it will close the steam supply. So in this way, if there is a time scale separation, this cascade structure will work way better than split range or load balancing. Because if we keep resistor around its center point in the saturation limits, then we will have the capability of fast temperature control and slow loop. In this case, this is the slave, and it uses the slow actuator, the slow dynamics, so it's a proportional integral low gain, because we have a lot of delay and large time constants. So this slave is slow, this master is fast, and then by trying to keep the resistor at its certain point, we try to keep the capability of fast temperature control, and only if the deviations are very large and during a lot of time, then the steam supply is modified to try to help the master resistor-based temperature controller. So this is how to solve this two manipulated variable problem with timescale separation. But of course, this operating point of 110 or whatever must be decided upon, dimensions, economical reasons, the cost of electrical heating versus steam heating. So, optimizing the operating point may need extra thoughts, but okay, this is the basic idea. In fact, if we put at this operating point 220, then suddenly we have a cascade control converted to a sort of split range. Indeed, this voltage controller, let's say, will only decide to open the steam supply when the command from the master temperature controller is above 220. So if we put here, let's say, a proportional controller in EC block, then we have an alternative interpretation of the split range. But this is kind of a discussion of the main topic. The idea is that putting this center point here, we are doing not split range control in the amplitude domain, but in the frequency domain, in the bandwidth domain. Fast corrections are carried out by the resistor, slow corrections are carried out by the steam supply. So this is extra actuator cascade control. And then the next option would be what we call gradual control. What does it mean? Well, I will now decide to buy an additional sensor to measure the temperature of tank 1, and I will use that sensor. So the new strategies will need to buy an extra sensor. But okay, you know, a temperature sensor is not expensive one. So let's assume we can afford buying it. Good. Then if I have this temperature sensor here, I may decide that instead of putting a set point of these 100 volts or whatever, I am going to leave alone this controller, so it will be master of no one. It will be an isolated loop, and I will try to decide with my process engineers on which should be the best temperature for tank 1. So if I decide a temperature for tank 1, then I would operate this steam valve with TC1 and leave TC2 for the tank 2. So this multi-loop strategy is called, let's say, gradual control, because we may decide, let's say, that if my reagents enter at 20 centigrades, maybe tank 1 is set to 70 centigrades set point, and the resistor in tank 2 needs only to increase it to, let's say, 80 centigrades. Well, then, as we are in a sort of multi-loop strategy, then this should work irrespective of having timescale separation or not. Of course, you know, the transients of controller 1 will be felt like disturbances, let's say, to control 2. But okay, we are separating temperature control into two, let's say, independent tasks, and each of them operates in its own isolated control loop. So this will be stage 1, and this will be stage 2, and this structure is quite used, let's say, for neutralization processes, or in, let's say, a lamination train in which we need to produce a millimeter thick steel plate by rolling it through a lot of rollers that each of them presses a little bit the metal plate. So, well, this is the gradual control setup, but the issue is that in here we kind of assume that these two set points are independent, unrelated, but that's not truly the fact, in the sense that, okay, look, imagine that now my operator, instead of 80, wants 95 centigrades. Well, in that case, this gradual stuff would do nothing in tank 1. So maybe we can have a sort of, you know, load balancing, so that if someone increases this set point, then I can increase this set point by, let's say, 50% of the amount of the increase to share the temperature increase. That would be a reasonable option. So it's kind of decoupling between those multi-loop terms, in the sense that, well, when something changes in stage 2, then I propagate the change to stage 1 in a fixed way. Okay, this is one option. This would still be called gradual control, but a different option would be setting this TT1 set point via cascade control, in the sense that, okay, if I use the first cascade structure we devised, we could think on deciding the intermediate temperature set point depending on how resistor 2 is saturating or not. So if resistor 2 is almost at full power, that means that temperature of tank 1 must be increased. So I can just send that extra temperature set point increment to this slave loop. So this is the double cascade configuration in which the generation of the intermediate setpoint for stage 1 is automatically carried out by this cascade structure. So this will be the master fast controller, and then this voltage controller trying the resistor to be at 120 will be the slave in the first cascade, but it will be the master controller in the extra sensor cascade by sending this slave of the slave a temperature set point. Then in this way we would be able to automatically compute the optimal temperature for tank 1 so that a lot of fast temperature control legroom is available in tank 2. So this is the double cascade structure, combining, let's say, gradual control in 2 stages with an cascade computation of stage 1 temperature. So let us summarize and conclude. In this video, based on a temperature control in a 2-tank process example, we have discussed how we can set up 2 control loops with an auxiliary set point and control variable when there is time scale separation, so that split range or load balancing, at least naive versions of them, may have some problems. So if actuators are similar in bandwidth, at least, because gain can be quickly corrected. The thing is that, well, for these similar actuators, then we have these options in the first video: load balancing or split range, override place in a separate league, it's kind of safety issues. But if we have very different technologies, very different time scales, bandwidths, then maybe we need the options in this video: cascade control with additional actuator, in which we set up an additional set point for the resistor for actuator 2, and then a slave loop uses actuator 1 to control, let's say, the low frequency behavior, slow behavior of resistor 2. This was cascade control. Then we had gradual control, in which, well, we decided an intermediate set point. So we carried out our task in 2 stages. We needed to buy an additional sensor, of course. And then the last strategy was realizing that the intermediate set point would need to change if the main set point changes. So we proposed this double cascade, in which the stage 1 set point was computed by a cascade control structure, so that when my customer requires higher temperature in tank 2, we will increase the power requirement for resistor 2, the voltage applied to it, and then this voltage control will realize that in order for the resistor to return to the center setting, we need to increase stage 1, tank 1 temperature set point. So with this double cascade, we were able to join the idea of 2-stage gradual control and cascade extra actuator structures. So either with these options in this video, with significant time scale separation and auxiliary control loops, or with these, in principle, simpler load balancing or split range strategies, all these options, we discussed a total of 6 of them, then all these options may help me improve the performance of control loops in which I have the luck of having more manipulated variables, more actuators, than controlled variables. So we finish with this. Thanks for your attention.